Oh, come on. All right, it is August 27th. This is ESM 105. This is lecture 2. Okay, so as mentioned, I'll be getting these recordings posted up, but they won't have the screen. I can't get both of them on the camera at once. So you'll have to kind of try to keep up. But it's a good, like emergency access thing if you couldn't make it to a lecture or something. But it will not be as good as being here because you just don't get, the vibes, man. All right. Anyway, what are we doing today? We're starting the class. On Monday, we went over the course structure, we went over the syllabus, I showed you how to use a citation manager so you can get that annotated bibliography together as easily as possible. Are there any questions about the course in general? We've got, we have time. If there's anything that I didn't make fully clear on Monday, or any lingering questions. Yes, please. Yeah.
Is it okay to how I feel taking class, or should I look for the topic?
Oh, for the topic, you can put for the discussion post, and just let me know if I'm not answering your question sufficiently, right? It can be a thought about anything that we've been talking about so far in the course. It could be something that you would like in the course. You can react to somebody else's. You might be the first one who posts. And if you do, you can't really react to somebody else's post. So you could say, boy, I sure do hope that John talks about green roofs, or sustainable building or something like that. And I'll look at the discussion posts, which will be nice for me, and then other people can react to your discussion post. Did that answer your question? Okay, awesome. Anything's good, just I want you to be engaged on a weekly basis with the discussion posts. And are people seeing those discussion posts as available? Yeah? No? They should be you should find them all under the discussions tab on Canvas. And they will be, week 1 will become available at the end of the week. So you do it post-Friday, right? Like it says on the Canvas page. Cool? So you do the discussion post each week on Friday. This increases the likelihood that everybody's engaging with it at around the same time. And that way, you don't have one post on Monday, and then everybody else posts on Friday, evening or something. Does that everybody understand? I don't think I really discussed the discussion post, so thank you for bringing that up. Any questions about that? There's one for each week. Cool? Awesome. If we just bop back to week 1 right here, what do we have to do? We read through the syllabus, look through the course calendar, start reading a Sand County Almanac. There are online sources for this. This book's been around for a long time, but there'll be a question on quiz 1 about it. Thank you. Hey. No problem. But there'll be a question on quiz 1 about it, and part of your final exam will relate to this book as well. So make sure you read the book. Cool. Question?
Will you use the books for the final?
I have to give you I'm not positive yet if I'm going to be doing the final in person or online. I'm leaning towards doing it online because that's how it was done in the previous semester, and I'm doing my best to stick with what the department has determined as a quality course. I'm trying to keep my changes minimal. So right now, it's probably going to be online, and I'm happy if you use the book. Yeah. I'll just make the decision. I'm the instructor. The final exam will be an online final, not in person. You will do it on Canvas, and I'm happy if you reference the book while you're writing your responses about each one. There you go. Cool. We did it. A decision was made. That's a big step for me. Only 5 years of therapy, and I got there. Thank you. Cool. Research project. You can start thinking about it. You can start assembling sources. It's fun if each week you just try to find a couple of good sources. In weeks 1 and week 2 of the lecture, I'm going to try to help you learn how to interpret the results section of an article. because that's something that we don't talk about a lot. In a lot of your classes, you'll talk about primary literature and its structure, but we don't really talk about how do we interpret the final statistics, which are what people are really going to be referencing. But anyway, look at the literature, post something on Friday. Any questions about week 1 or anything else? Solid. The PowerPoint is right here. Get off of here, come on. Don't need that. All right. Natural resource conservation. Let's try to get this light situation under control, because that's a little intense. How's that for people? Daylight? Awesome. Okay. Week 1, week 2, we're going to cover this PowerPoint right here. All right. We did this course outline stuff. I'm your instructor. I'm John Montgomery. It's so good to meet you all for the second time. Okay. Canvas page structure. We saw it. We reviewed the syllabus. Discussions, the quizzes, the annotated bibliography, the final exam. As I said, we just made the call right here today. Decision made. Final exams online. It'll have some essay questions about the books. It'll have some multiple choice questions. You'll get used to the assessment material as you do the quizzes. Quiz 1 is, I believe, in week 3. I'll send out announcements and updates to try to keep you on track with all that stuff. But your to-do list and your calendar on Canvas should also all be populated if I did my job right. And sometimes I have made mistakes, but it's not going to happen this semester. No way. No way. Citation managers, okay? We talked about them. Zotero, somebody mentioned as what's been promoted a lot around the campus. That's awesome. Zotero works. It's good. I like EndNote Basic because it's what I was taught to use, okay? But a citation manager will make constructing your annotated bibliography easier. Cool. And if you ever want help with something like that, I got office hours. I also have a little window of time after these lectures, and you could come talk to me, or we could go to my office and talk, usually. Okay. I did not assign this textbook to you, but it is the textbook that I'm using as a foundation for the course. All right? So, figures, some text I'm typing out of the textbook, It's just good to organize your thoughts as an instructor with a textbook that you've deemed to be of sufficient quality. This textbook was pretty good, It's pretty good. I screened like 4 different books, and there's a lot of bunk out there, but I like this one okay. McGraw-Hill's an okay publisher. You can get online access if you want to get access to this. It wouldn't hurt to be referencing this. If you do end up referencing this textbook or checking it out from the library or whatever, all right, you'll find that there's a lot of similarity to the presentations I'm giving you, because this is, full disclosure, the foundation of the course that I've built around. Cool? I want to make this apparent, just in case you want to be like, I want some practice quiz questions. I'm going to find McGraw-Hill Environmental Science and Global Concern practice quiz questions. Cool? Awesome. Okay. So this is a really standard sort of figure at the beginning of each textbook that you encounter. It'll be like, what's the field? How does it connect to all of these different sections or segments of society, including, we've got here some chemistry talk, ecology talk, humanities talk, policy talk, all right? This all has to do with environmental science, all right? And if you're involved in natural resource conservation, then you are going to at least need to interact with people who are environmental scientists, all right? So we're gonna cover a bunch of these different aspects, including a basic chemistry review, okay, so that we can understand the toxicology section of the course. We're going to talk about economics. We're going to talk about, I don't want to really call them non-pragmatic concerns. That's a pretty crazy way to say it, all right? But like cultural values, anthropological value, religious value of ecosystems, of natural resources, all these things will matter and intersect and be involved. Okay? You're gonna see that I do a lot of big text slides. It's because I want the PowerPoint slide to be a resource to you. Okay? So you can go back and read the slides and get the key information. I'm going to not stand up here and read the whole slide to you, but they'll give some background that you can look at, and they'll be really useful if you miss a section, or if you just, want to go through the material at a more leisurely pace. So you'll see, if you compare this to our syllabus, that a lot of this stuff syncs up with syllabus topics, all right? Biodiversity loss, we're gonna talk about that. We're gonna talk about water resources, all right? We're gonna talk about different types of pollution. There are all these themes in environmental science, okay? Signs of hope, wonderful, we can make changes, right? There are chances that, changes have been made that recognize the importance of the environment. And usually these policies are implemented because of entirely pragmatic concerns. We'll talk about ecosystem services, things that the environment provides that we cannot provide ourselves, or from the most cynical perspective, things the environment provides that it would be cost prohibitive for us to provide ourselves. You see what I mean? Things like, we can just implement desalination plants and then redistribute water across the country. You could say that's cost prohibitive. All right? The infrastructure's too complicated. We can't do it. So, okay, I guess we need to protect water resources. It's a cynical, pragmatic view of things, but you will interact with people who have a cynical and pragmatic view of things. And sometimes that's the motivation that gets the conservation effort implemented. All right? Solid. So this slide includes things like carbon markets. We'll talk about carbon markets, the issues with them, the benefits of them. I've got I don't have a vested interest. I didn't invest in this company. Well, I've done a bunch of research with biochar, a bunch in my career. Okay, and biochar, the viability of that market is tightly tied to carbon markets. I'll just briefly talk about this. The idea of biochar. Who's heard of biochar at this point? Okay, cool. We've got a number of people. They're really trying, for the last 10, 15 years, they're really trying to make it a viable product. You'll see it sold in Home Depots and in Ace Hardwares as a soil amendment. It's got all these promises. I've done a lot of research with biochar and turfgrass in an attempt to reduce turfgrass irrigation requirements. How do you generate biochar? You pyrolyze organic matter. You put organic matter in a kiln, all right? You burn it in the absence of oxygen, and you get all of these stable carbon compounds. And sort of the goal, this is very oversimplified, of course, right? But the idea is you get this carbon sponge that you can then incorporate into the soil. It'll hold on to water. It'll hold on to nutrients. It reduces fertilizer runoffs or run-throughs through the system. It reduces irrigation requirements, and it sequesters carbon in the soil. Now, we're going to talk about the carbon cycle probably in week 2 and what exactly carbon sequestration is. But the idea is carbon-containing compounds in the atmosphere act as greenhouse gases. Plants take those carbon-containing compounds and fix them into stable forms. If we can get those forms to stay stable and then bury them in the soil where they can't decompose, all right, then we just sequestered carbon out of the atmosphere and put it someplace else. So there's an entire market arising with trading in carbon credits. Arcata Community Forest is, I think, the first county managed forest, something like that. It has some claim to fame of selling its land as, you buy the carbon credits and we promise not to develop this land for X years. were they ever going to develop that land? Probably not. Is it good that a company now gets to offset carbon emissions by paying the county or whoever's managing the community forest? Probably not, because now they get to say we had net zero carbon emissions because we bought the rights to not develop that forest. But does it look really good when you buy a bag of kettle chips and it's like, oh, this bag of kettle chips planted trees? All right. So anyways, you make a market. You try to make a market where trading within that market generates sustainability. That's one way of pragmatically trying to get at this stuff. Okay, next slide. Historical perspectives on environmental science / conservation. All right? This is going to move from very, very pragmatic roots. And most sciences, I just talked about it to you once. We don't know each other that well yet. My background is in, my background's all in plant ecology, plant physiology, but my lab that I worked in for 6 years where I did all my research was a turfgrass lab, all right? It's entirely pragmatic work, okay? Where you're just trying to find which of these chemicals can we put on the turf to make it cost less to maintain, to keep the golf course members happy, to reduce ankle breaks on sports fields. All of these things are well-funded fields of study because they are serving a very pragmatic purpose. Now, all of science, right? Not all. I'm going to be hyperbolic here. Biology, ecology, botany, all of these different subfields, okay? They all initially arise from agriculture, usually, because people wanted to understand how to manage crops most effectively for the greatest benefit. It's an entirely pragmatic perspective. What do we do to manage this artificial ecosystem or a very natural ecosystem in early agriculture, right? What do we do to manage that to get the highest yield of the things we want? Do we regularly burn? Do we keep certain animals out? Do we try to encourage certain animals to be here? How often should we harvest? And that leads to an understanding of how biology operates, of how animal breeding operates, of how plant breeding operates, of how agriculture should operate, all right? So our beginnings are pragmatic, and they're usually credited to they'll be put on Theodore Roosevelt and Gifford Pinchot, all right, in the United States as the beginning of a conservation movement. So there's this work called Man and Nature, all right, written by George Perkins Marsh. And you read it sometimes in certain classes. It was more prevalent to read it before my time, all right? But we still read it a little bit in my day. Yeah, please.
In this context, what is the word conservation being used as? Like conserving from what?
Conserving from development, or really, if I'm being fully honest, moving natural resources into government control instead of having them be under private control where people can do what they want with them.
So the government is regulating the government.
Exactly. Yeah.
Works out well.
It works great. Don't worry about it. Don't even worry about it. Yeah. Yeah. All right. So we've got this initial work, Man and Nature. It gets a lot of publicity. It says, oh, humanity is transforming nature. Nature's transforming us. We have the power to destroy the environment that we need to survive. All right? Theodore Roosevelt, Gifford Pinchot cite this as foundational for establishing conservation efforts in the federal government. All right? So Pinchot ends up being the senator of Pennsylvania after being the first head of the Forest Service, which had an additional name before that. Here he is. All right. There we go. Pinchot, there's Theodore Roosevelt. So early 1900s, big conflict called the Pinchot-Ballinger controversy. All right? So Theodore Roosevelt doesn't get reelected. Instead, it's, oh, my history gets all twisted up. It's Taft, all right? Taft gets elected, okay? And Taft has these advisors. Hey, has this advisor, this Ballinger guy, who's like, let's just put all these things into public, or into private hands, all these resources. They can manage it. What are we doing managing these vast swaths of land as the federal government? Why are we doing this? Okay, so public land gets reclassified for private use. A bunch of really, really nasty stuff gets discussed in the public discourse. Okay, you can look into it on your own. This was a really big deal, and that led to fights, like physical altercations. It was a big mess. Okay, but eventually, it sort of resolves itself in bringing to light for the public this idea that all of these forests and all of these big swaths of land are going to be under private control. And do we trust the private industry and the private owners who are going to be owning all this land? Right? They can just develop it. We need it. Okay? So that's our pragmatic resource conservation phase. All right? Where the idea is manage the forests, help the most people we can for the greatest amount of time. All right? Cool. Stage 2 moves on to ethical aesthetic. All right? Where people are arguing that nature has an intrinsic value. The natural system has an intrinsic value. Okay? Either it's aesthetic, it's cultural, or you say that it's just ethical for us to be not developing everything. All right? Leaving natural systems undisturbed. Do we have an ethical imperative to not destroy? Okay? To conserve, to maintain. This is our second stage of conservation and environmental science, sort of. It's like, is it good enough just to conserve? Or, from that previous perspective, does there need to be a greatest good for the greatest number of people? Because if this is your motivation, well, people need houses, people need places to live. So we're managing this forest, we need to cut it down and turn that into houses. And you argue that that's the greatest good for the greatest number of people. So now this moves us into stage 2. As I mentioned before, we've got John Muir, we've got Aldo Leopold, all right? Who wrote Sand County Almanac. You're going to be reading that one, right? Okay, great. So yeah, our next stage was it's ethical to conserve. We don't need to develop everything. There is a value, an intrinsic value to the environment. Solid. An intrinsic value, I should say, to natural systems. Naturally developed systems is how, as a scientist, I'll say it. Okay? And we'll talk about systems and all these sorts of things later. Okay, there's Roosevelt, there's Pinchot, there's Muir, there's Leopold. Next, modern environmental movement, okay? There's more. World War II happens. Industrial Revolution. More money, more activity, more development. Things are flowing around. What do we do? Okay? More conservation, more students of or intellectual followers of that ethical conservation sort of rise to prominence. We've got Rachel Carson's, a really big one, Silent Spring. Remember this? World War II brings about all the invention of these pesticides and herbicides and all these chemicals, okay? Chemistry gets advanced in huge leaps and bounds, and we start just using pesticides to control insect populations, modifying our natural environment in a pretty pragmatic way. I don't like a mosquito. Nobody likes a mosquito. Okay? So we spray a chemical that kills all the mosquitoes. What could go wrong? All right? All the birds have a problem, or their shells are too thin. The birds don't survive. No good. Okay? Silent Spring, Rachel Carson. Classic foundational conservation book. Cool? We've got group350.org. That was pretty popular for a while there. I don't know if people are still using that resource, but Bill McKibben we've got here. And then we've got Dr. Wangari Maathai, who founded the Green Belt Movement. So we've got international conservationists active as well. Okay? Modern environmental movement. You've got people trying to understand more of the complexity here. Okay? What you're kind of seeing is a trend from we're just managing it pragmatically. No, we're not doing anything to it. We have an ethical imperative. We have an obligation to not develop, to not change the natural system. That's something we need to conserve. It's our obligation as thinking creatures who can modify our environment. To the next step, which is, listen, there's serious concerns if we don't conserve certain aspects of the environment. Serious concerns with climate change. Serious concerns with the integrity of food webs that we still rely upon to deliver stable ecosystems that provide us ecosystem services that we just can't provide for ourselves. Okay? And then global environmentalism is what the textbook lays out as the fourth stage of environmental science and conservation, okay? Which is really more about interconnectedness, okay? So it's easier for local organizers to gain prominence. It's easier for people to communicate. It's easier for people to reach an audience who don't necessarily have traditional classic credentials. So now you have people who have what their communities have deemed to be good ideas interacting with other people who their communities have deemed to have good ideas. All right? People with different approaches to conservation, people who haven't gone through, 12 years of academia or 30 years of government service and still, still are able to think outside the box a little bit. So, yeah, global environmentalism is really boiling down to more interconnectedness. It's all about that dang old internet, social media. Your textbook goes into a lot of detail about that. Okay. I screened 4 textbooks for this course. They all lay it out in about this same sequence, and they all show a picture of Greta Thunberg with stage 4. That's their, demonstration of global environmentalism. Okay, solid. Now we are moving in away from our historical perspectives and the evolution of natural resource conservation thinking. All right, and of course, there are still, yes, please.
So before stage 1,
Yeah.
is there anything to do with humans and their environment?
Yes, humans have had to interact with their environment. There's different thinking, but we are discussing sort of codified large scale in the US natural resource conservation. Huh? Yeah, colonial, yeah.
Based off of indigenous practices.
Yeah. Stupendous. Okay, so moving forward, we have passed through the historical stages here, and now we're into the, now we're into the next section of the course. Let's go with that. All right, great. So, environmental concerns, income. We have people in different income classes. We have countries in different income classes. There are inequalities in wealth on small scales. There are inequalities in wealth on large scales. All right? And this leads to inequalities in conservation. okay? The conventional wisdom is if you have excess wealth, then you can externalize your environmental costs. You can develop more and put all of the environmental costs into other areas, okay? Whether that is county by county, within the county, between the states, between the countries, all right? Whatever that is, okay? So that's what this figure right here is sort of trying to get at. Low-income communities, right? They become victims of environmental degradation because higher income communities or countries externalize their environmental costs there. Also, all right, they tend to become agents of environmental degradation because they do not have the access to implement environmental protections, and priorities are more towards survival, okay? So we've got victims of, agents of environmental degradation, okay? So yeah, water contamination, urban air pollution, greenhouse gas emissions. The idea here is that, look, water contamination, as you increase wealth, it tends to go down, all right? Greenhouse gas emissions, as you increase wealth, tend to increase, all right? There are a lot of conveniences and quality of life things that emit a lot of greenhouse gases, okay? Then we've got the urban air pollution here, problem right in the middle, where as you increase wealth, you tend to increase air pollution, and then you move towards different practices that may be increasing greenhouse gas emissions, but don't lead to the same smog issues. And these are broad trends, of course, that we'll investigate in much more detail around week like 11, I think, of the course when we talk about pollution. Okay, good deal. So this is basically a rewording of what I've just said to you. Wealthier nations consume more resources per capita. All right? So this third bullet point right here, if all the residents of China were to match American consumption rates, you'd need 4 extra planet Earths to to sustain. All right, that level of resource consumption. Question, please. Okay, I'm sorry, can you please repeat the question?
Where does the excess resource consumption originate from? Where do the resources originate from themselves? The oil, the carbon dioxide, and where do things come from into the U.S. into the hands of the consumer?
So the idea here is you've got, well, for one, no, there's international trade and movement of resources as well. Okay, thank you. So, US consumption rates, all right? There is trade of resources and there are trades of waste products, okay? Some countries can be motivated to accept waste products, and that's another problem here. Different countries have different population densities, all right? There's this concept, which is about to come up here, of cultural carrying capacities. So, the planet, right? How much can the planet sustain? How many people can live on the planet? That's the big question in conservation, right? How large can our population get? Because populations continue to grow, most folks don't want, I'll avoid that. Human carrying capacities, okay? Classic question in ecology, classic question in conservation, all right? Physical or biological carrying capacities, the first one. This is defined as how many people can we pack? And there are tons of different calculations that estimate different carrying capacities for the planet based entirely on physics, available resources, etc. Technology can increase carrying capacities, all right? The most interesting, the most probably comical, actually, carrying capacity calculations relate to how much metabolic heat humans generate. And if you have enough humans on the planet, you'll literally raise the temperature of the Earth to the point where it just, isn't sustainable anymore. But more realistic carrying capacities have to do with estimating how much space each human needs. Yes?
This might be kind of a dumb question.
No way, don't worry about it.
Do you think that metabolic heat is currently impacting at all? Or
No,
no?
at least not significantly, right? Yeah. But no, it's a good, yeah, there's so much more that's affecting this. It's such a small factor. There will definitely be an impact of it, but with the rate at which infrared radiation leaves the atmosphere, yeah, I wouldn't worry too much about that. So yeah, so don't work out because you're raising your metabolic heat, right? Cool. So we've got physical carrying capacities, right, which are set by what does a human need. The idea is it's set by like the bare bones to survive. How much space do you need when they're setting these calculations? How much land do you need? You know? But then we look at cultural carrying capacities expressed in the same way of like, how many square meters of land does it take to sustain a person? All right? And from country to country, that number varies drastically. All right? Where it takes a larger landmass to sustain somebody in America on average than it does to sustain somebody in India on average. All right? And that has to do with cultural acceptance of sort of quality of life considerations. You know? Air conditioning, things like that, electric lights, all these sorts of conveniences or necessities depending on where you're at, right? So an accepted range for K is 10 to 20 billion people. What's K? K is the carrying capacity. And this is ESM 105, so my assumption is that you haven't really had to discuss population growth rates and population models yet. But I'm gonna address that right now. By now we're gonna move into straight up population modeling. It's gonna be very exciting. So K is a variable that represents carrying capacities for a population. Ready, folks? Let's get into this is going to be very gentle math. All right? So, what is K? Okay? Modeling. I have slides coming up to you all about modeling. Modeling is how we understand the world around us because we can't understand every single factor that goes into changes that we see. If we want to predict how conditions are going to change in the future, we need to generate models that deal with the environmental variables that we are concerned with. And we need to discount things that don't affect our important variable. So if we're concerned mainly about increases in temperature, we're not going to be considering every single aspect of the environment in generating models. Modeling is the way that scientists deal with their environment, okay? The way that scientists deal with systems, from the cell to the organism to the ecosystem to the biosphere to the solar system, all right? Models change, variables are adjusted. Cool. Like we don't look at cellular respiration rates in a model that's predicting the movement of mercury, even though everything is, connected. And you could build a model that incorporates every single aspect. It wouldn't make sense. Okay, good. So a very basic model of population growth. Standard issue, logistic model of population growth. What we've got here is a sigmoidal or S-shaped curve. This proposes that each population, all right, will grow rapidly, all right, eventually hit what's called an inflection point, where it's reached a stable sort of population growth rate. Population growth will then slow over time as you approach K, the carrying capacity. So there are two important variables in this model, and we're just going to look at the model. This is like a scary thing to just pop up on a slide when so far we've only been talking about, conceptual stuff. But trust me, we'll get through it. Yes, please.
What is 1 unit of time on that graph?
It's usually a year, but the model can be adjusted for any time scale. If you're modeling E. coli population growth, you're not doing it in years, because in 1 year the population just stays like a flat line, because it's probably going to go boop and hit carrying capacity and then plummet eventually. You know what I mean? Yeah. So time units, the units for this, can be adjusted. Seconds, days, weeks, years. All right? But usually when you're dealing with ecology papers, or at least ecology textbooks and environmental science textbooks, T equals year. Okay? Or units for T is years. I love it. Okay. So look at this complicated looking equation right here. Let's just dissect it for a minute. Delta n over delta t, or dn over dt. Same thing. The delta symbol represents change or difference. Okay? The delta symbol's a little triangle. It's named after river deltas, right? River deltas are sites of great change depending on how much effluent comes through there. Season to season, you could have a lot of productivity in the delta region or no productivity in delta regions. So there's the beautiful roots of why we use delta to represent change. So we've got delta, why am I using this? I have a laser pointer. We've got delta n over delta t, or dn over dt, depending on the shorthand you're using. It's equal to r sub max. What I mean is we've got an r with a subscript of the word max. So if I say r sub max or n sub t or something like that, it's just a shorthand, all right, because we use r as a variable for many things. R is the intrinsic population growth rate, or the max growth rate that the population has. Okay? How rapidly can the population grow? How rapidly can the population grow if nothing's slowing it down? So what's its max population growth rate? N is the current population size, okay? And then we have in parentheses 1 minus n over k. So if k is the carrying capacity, here's what this means, all right? Let's say that your maximum population growth rate, let's get this all to pop up. Max intrinsic rate of increase, r under ideal conditions. Inflection point is the steepest slope, right there. When n is low relative to k, all right? So if our r sub max is, let's say, 1.1, all right, it means that the population from, assuming t is years, that the population from year to year goes up by 110%. So the population, if r sub max equals 1.1 and our initial population equals 100, all right, well, then if there's nothing stopping the population from growing, next year the population is going to be 110. Because we're just multiplying r sub max times n. Just that straightforward, all right? But modifying that growth rate, we have this parenthetical term right here, 1 minus n over k. So check this out. Let's say the carrying capacity of this population is 200 individuals, all right? And our population is currently 100 individuals. That means that we're going to have 100 over 200, or 0.5. 1 minus 0.5 equals 0.5, all right? So effectively, the change in the population will be slower. The population will grow more slowly, all right, because you're nearing the population's carrying capacity. Yes, please. D right here, difference. It's just another way, because textbooks will sometimes use delta and sometimes they'll use D, and publications will too. So I just want you to be prepped that you might see it presented either way. But delta's the best one. It's the coolest one because it has that fun history of like river deltas. Yeah?
Sorry, I'm not sure I quite understood what RMAX is. Is that like
No
the
problem.
rate in growth of the
Yes.
population? Okay.
Yes. So the idea is if the population's the maximum growth rate of the population, if it's like 1.1, then that means from year to year, the population increases by 100 to 110% of the population that it was before. It's the max growth rate if nothing's limiting it. And carrying capacity is meant to incorporate all of the things that limit population size. Question, please.
So if you multiply 1.1 times 0.5, you would get 0.55. So would that mean it just goes up by 5.5% instead of?
It would go up by 55% of the population size, because the delta n over delta t is the difference in population size. So here's what happens. It's an increase of 55. And I think I might have actually said, oh, the population would be 110 previously. What I meant was the population would increase by 110 individuals. Thank you for catching that, because that's a big mistake on my part. So the population, if there's no carrying capacity in effect here, would go up by 110 over the year. And if the population is at 1/2 of its carrying capacity, it would go up by 55 over the following year. Thank you. I got it. Yes. And do you have a question too? No? Okay, cool. Yeah.
So the change of population per time is slower the closer it is to the maximum carrying capacity.
Exactly 100% points. Very good. And if the population exceeds the carrying capacity, right? Let's say the population gets up to 400 individuals, okay? And the carrying capacity is 200. Well, now it turns this into a negative term, okay? Because that would be 1 minus 2, -1. So now the population is going down. So what this model predicts is that the population will essentially do this. Do I have it on a slide? I'll do this. Here we go, 1 second. What the equation actually predicts is that populations will start small, eventually hit a max growth rate, and then level off. Okay, but if they exceed the carrying capacity at all, they'll go like this. And that's what actually happens in a lot of systems, right? Or in a lot of populations. The population goes up, and then it fluctuates predictably around carrying capacity. This is a very simple model, all right? And so it's not going to perfectly perfectly predict population growth and population change over time. And oversimplifying things by just putting up K as the carrying capacity, it's like, well, how do we determine K? What goes into K? And the carrying capacity of a population is determined with humans, not only by environmental constraints, but also by cultural constraints and cultural norms. And that's where we end today's lecture. And we'll come back on Friday, and we're gonna just crush basic scientific literacy stuff. Thank you all for being here. It's been a pleasure as always, and I'll see you at the next lecture.